Okay, so without any further delays, let's start with the session. So next talk is by Carsten Weinhold, the principal researcher at Composable Operating System Solution at Barkhausen Institute, Schweden, and he will enlighten us with the modular approach for trusted execution environment. So,
this is actually just the first part of the talk, but it's also kind of the whole context of the work we are doing. The second part is actually a paper that is currently under submission about combining transport layer security and remote attestation, and people who collaborated with us on this are mostly in the room, I think. Okay, so first about why we would like to have modular TEs. So we all know that there are quite a lot of TEs that we can choose from. So from the big vendors, and there's also a lot of research being done, and doing some open source implementations here and there. But even though there are so many, you don't really have that much choice because they are typically tied to one specific instruction set architecture. Like x86, for example, you can have that from AMD and from Intel. You can, for example, have SGX with an ARM CPU or with RISC-V. The actual implementation of these TEs is typically inside of a rather complex core. So, and that has a number of problems, as we all know. So since a while ago, we know that there are speculative execution attacks that make life harder, and some of them even target TE implementations such as SGX. So using some of these attacks, SGX kind of has to be regarded to be broken. So that's also a big problem if they are integrated into these complex cores, and things are not really changing, at least some manufacturers in that regard. Then there's also various types of keys you can have. So there's something like an enclave. And when you have something like that, you typically need a library OS or some kind of wrapper around the operating system outside in order to have some interaction with the rest of the system. With VM-type TEs, this is by design not a problem because they are standalone, but then it's also hard to have interaction with the rest of the system. So these are things that, depending on your use case, you might want to have, but you only get the whole package. So the problem we see is that TEs and ISAs cannot be chosen independently, that they are tied to core microarchitectures that have functional problems and other issues due to complexity. And there's also a lack of good integration with the rest of the system and the system software in general. So that's why we thought, why does it have to be like this? And if you want to change it, how could we do this? So we kind of would like to have something like modular TEs. And to answer the question what a modular TE is, we first have to think about what is a TE. So at least to us in our group, a TE is about protecting some application. So we have an application, and you put it into kind of like a box where it's isolated and protected from applications that are also running on the system or other activities, including attackers that have physical access to the system somehow, depending on the attacker for the specific platform. But typically, applications also need to cooperate with other applications, maybe on a different machine. That's why we have to break little holes into those isolation barriers. And TEs also typically support something like remote attestation. You all know that. So you ask, what is your state? Send along a nonce in order to ensure freshness, and then you get back a response that is the attestation evidence or a quote, whatever you call it. And this includes a measurement of the application that is running in there, along with some metadata typically. And this is signed by a root of trust that is also part of the system. So these components, they are important, and they kind of define TE-capable platforms and what a TE is. And we identified 6 concerns that such a TE implementation must provide. The first is obviously the computation. Sorry about this glitch. That's also I had to export this in order to avoid the HDMI trouble. So there's computation that's about having a core memory to execute the process or the program. And then there's measurement that we need in order to figure out what program is there. We need the root of trust in order to sign that measurement and provide the assurance that some software is running in a certain state and also that it's isolated, so we need isolation. So that's another concern or thing that such a TE needs to provide. And then there's the whole lifecycle management that you have around it, how you start programs in a TE, how you shut them down, what happens while they run, and so on. And the sixth concern is what we call the environment. That is basically, what is the interaction with the outside world looking like? What kind of communication is allowed? What is allowed? Can you do I/O? That sort of thing. And obviously, the various implementations, they differ in all of these aspects. And typically, when you have such off-the-shelf implementation, everything is one big piece. So everything is kind of lumped together. And you cannot really change anything, not even the firmware, as we just discussed after the last presentation. Some implementations already try to isolate things a little bit. At least AMD, for example, is isolating the compute part and the isolation part, which is running on the x86 cores. And then we have management, measurement, and the root of trust implementation, which is implemented on a secure processor that is next to the application cores. Ideally, we would like to have this kind of separation also for all the other concerns in some way where it makes sense. And even better it would be if we can actually mix and match the individual parts, that we can choose the type of TE and how measurement works, independent of the ISR, and so on. And also what kind of isolation primitives we require and how they are implemented. That would be really nice. So this is kind of just a motivation about why this might be useful, and we are working in this direction in our group. Actually, this is part of a paper where we also talk about how we try to accomplish this modularity by building a TE on top of the M3 microkernel platform that we are developing at the Barkhausen Institute. So I'm not going to talk about this. You can read about it in the paper or we can chat afterwards. In this presentation, in the second part, I would like to focus now a little bit on the environment and especially the communication part. Because part of the environment is how the program inside the TE can communicate with the rest. We also need measurement and root of trust a little bit there, but that's basically that it's necessary to have. All the other stuff is currently not so interesting. We of course need it, but that's not important for the rest of the presentation. So how do we ensure secure communication? So TEs provide attestation, so we kind of get an assurance about what's running inside the TE on the right-hand side for us. So we get this attestation evidence, and we can inspect it or ask our verifier, and then hopefully we decide that this is okay. But this is kind of a snapshot in time. This is the state at the time of attestation. But typically afterwards, you want to have further interaction. So you want to talk to the program that is running in the TE. And how do we do that? So TLS is kind of a protocol that you can use that is fit for very many use cases. So that's why we looked at it. So it's also kind of battle hardened and actively developed and so on. So it's rather nice. So we would like to have it. But now the question is, how do we combine this? How do we integrate this with TEs and attestation? This is what this second part of the presentation is about, how we can achieve this. So somehow we need to combine the two systems, transport layer security and attestation. So TLS is a protocol that starts with a handshake. Starts with the client, the computer on the left-hand side, by sending a hello message, and the server replies with a server hello message. and also with a message that is containing the certificate that identifies the server. The server may also ask the client to present its own certificate, which the client can then do, and then we have mutually authenticated client and server, and they from then on can communicate with each other through a secure, cryptographically protected channel. And remote attestation is also a protocol that is also kind of performing a handshake. The client, in this case, would send an attestation request. The reply would be a quote or attestation evidence, and it could ask for an attestation report from the client as well, and then you get that quote. And this structurally obviously looks kind of the same. So the idea is that you could try to merge these two protocols, or at least run them at the same time. So we would now ask for both the attestation report and the client, so we send the client hello and the attestation request at the same time, and the server can reply with the server hello, and also with the certificate and the quote about its state. And then same thing, server can request both the client certificate for TLF and also the attestation report. So this is quite nice because this saves us additional network round trips. So we can perform these two handshakes at the same time. It would be really cool if you could. So how can we do it? TLS already supported for a while message extensions. So for each TLS message, or selected ones, you can add extensions that's extra payload where you can put additional data. And we can use this in order to attach, for example, the attestation request to the client hello message. And then TLS will take care of sending this message with our attestation requests. So the RA, the remote attestation pod, doesn't have to do anything extra. It just needs to somehow append those messages in the same for all the other extensions. So we published this a while ago at the workshop, but we are not the only ones who had this idea. In fact, people in the room we are working on standardizing this idea along with other stuff. So there is an active draft proposal that is being worked on how to standardize those message extensions for remote attestation. So that part is really nice and seems to work for many people. So what kind of properties do we get? So we looked at related work that also tries to combine TLS with remote attestation. So that's the systems that you see in this table. And the property that we have by combining those two handshakes is, for example, that we don't have these added round trips. So not all of the protocols or the alternatives do have this, but this approach apparently sort of solves this. Also, it does not add any additional encryption. So once the channel is established, we basically use all the TLS crypto that has always been there. So there's nothing extra, at least for some implementations. So that ticks check boxes for having potentially good performance, you could say. Now, it's not really combined yet. We are doing it at the same time. So how do we combine it? And the problem that we need to look at primarily, I would say, is the problem of man-in-the-middle attacks or relay attacks. So TLS is already protecting against this. So if there's some evil talking in the middle that tries to intercept messages, this usually doesn't go with TLS. It's still to avoid this. This is based on assumptions, like, for example, the TLS implementation on the server has possession of a TLS private key, which it uses to sign the messages, and the protocol essentially takes care of protecting this, this channel. When we combine it with TLS, when we combine it with remote attestation, how would that work? So the critical part here is the handshake. So if the attacker tries to intercept the handshake, the attacker would then have to send another hello request to the attesting party on the right-hand side. And then, of course, we get attestation evidence, and now we somehow need to link it to the TLS plot. So one way to do it is we can link it to the TLS private key. by, for example, including a hash over the public key in the attestation evidence, and then we can compare, the verifier can compare this and make sure that this channel is using the same key, signed by the same TLS private key, and this is also included in the remote attestation evidence, so it must be coming from the same machine. So, and then now, obviously, there can be a secure end-to-end secure connection between the attacker, Eve in the middle, and the application on the right-hand side. And then Eve cannot do really much without it, so it could not establish another end-to-end secure channel with the application on the left-hand side. So that kind of works. But it's also working based on an assumption, and the assumption is that we don't have some horrible attack like Heartbleed, for example, that allows us to clone the TLS private key, or maybe there is a bad administrator who somehow got access to the private key and leaked it. But if this exists, what does it mean for the combination of TLS and remote attestation? So Eve can now be evil again, and Kia now has a clone of the TLS private key. And this means that she can just forward the attestation evidence, and this is now to the party on the left side, the same evidence. It looks like the evidence comes from Eve itself, but in fact it is not. So we have two end-to-end secure channels, well, secure. We have two TLS connections. It looks like they are between the two applications on the left and right-hand side, but they are not really. And the problem is we have now an evil peer here that we should not have. There could also be evil software running there, because the attestation report is only attesting what is running on the machine on the right-hand side, but not what is running on it. So the issue that we have here is if you use a construction like this, we kind of, if TLS breaks, attestation breaks as well. So, and this is not a nice property to have, because actually we want to use the two protocols because we want to make things more secure. So instead of just having a secure connection, you would also like to know what is running on the other side. And this part completely fails now. So this is not very nice. And part of the problem here is that we use one of these potentially long-lived secrets, and that could be, and that makes the whole construction fall apart. Actually, yeah, so the basic man-in-the-middle problem or relay attack problem gets solved by all those related works, but they do not necessarily fail independently, like in the example I just discussed. This is when TLS fails, attestation fails too. But it would be really nice if they fail independently. So it's not as secure as the least secure protocol, but it's as secure as the most secure protocol, you could say. It's not entirely that because they are doing different things, but you get the idea, I suppose. So what else can we do? So TLS already has some other secrets that we could use to link to our remote attestation in order to make sure that those two are actually terminating in the right machine with the right software. And what is happening during the handshake is those messages are sent and they have interesting information, like, for example, nonces. So we have nonces that are from TLS, and we also can add our own nonces for remote attestation. But there's also these DHE client things, and the same for the server. So these are public key shares for the Diffie-Hellman key exchange. And the key part here is that's ephemeral. So that means it's generated each time during each session. So what's the question?
In your previous slide, we were talking about the long-term key that are leaked in the server. It's the one that signed the certificate in the server.
So obviously you can do things to protect it, but So there's also this other secret that is being computed, and the client and the server can compute it based on some public call that is exchanged using those messages, and they both compute the same secret, which is this PHE. And by construction, that's how the protocol works, or the key exchange works, is only those two parties know about the secret. This is what TLS is using in order to secure the connection and encrypt and so on. And it's also doing something with the messages. So it's keeping a log of all the messages that have been exchanged, and it's computing independently on the client and on the server side a hash over this. So this is called the transcript hash. And this is updated a few times. But both the client and the server can compute this hash, and they can use it to confirm that they are basically seeing the same messages. So it's the same public key shares, for example, that are being used together with their private parts of the keys that end up creating this Diffie-Hellman shared secret. TLS then essentially signs this transcript using its private key, and this is how it makes sure that the communication channel actually ends in the machine that is in possession of the private key. And we thought we could use something similar for the attestation part. So we just take what TLS computes internally, this hash, and we hash it too. We additionally also hash the shared secret, and this is then a different hash, obviously. We call it the linking hash. That is used for linking against the attestation evidence. And the reason why we include the shared secret as well is that for TLS, if you don't hash it, it will fall apart because the wrong key is used, so the messages could not decode and so on. But this is not the case for remote attestation, so that's why we add this part of the internal state that can only exist in the two parties that actually perform the protocol. So, and this is then signed by the root of trust. So this is kind of the end result. So the yellow part is what TLS is doing. So we have an endpoint ID, which is something like a domain name if you use it for a website. And this is signed using the TLS private key. So this is still unmodified TLS. And what we add by this construction is the linking hash, which is just using state that TLS computes internally. We just take it. And then we sign it via the root of trust, essentially, and include it into the attestation report. And now we have two independent trust anchors that link to the communication channel that is then using those Diffie-Hellman derived shared secrets in order to protect the communication. And obviously there are also the nonces in there that guarantee freshness, and they are included in all of these messages that end up in the transcript hash and the linking hash. Yeah, so this is the basic idea. And if we do it like this, we can actually markedly get all those nice properties. So we have no added round trip and added encryption, so performance is good by interleaving those handshakes and piggybacking them on those message extensions. And it's failing independently, at least we think. And also another property is independent deployment. So there are people who are thinking about merging attestation and TLS, certificate handling and so on. But you don't necessarily have to do it. Because if you keep it separately, if you really run it in parallel, it's modular. You can add remote attestation while still using the old TLS-based certificate infrastructure, and it's independent. So that could help with adoption. So that's, that's hopefully nice. So to summarize, the broader context of our work, and I think maybe also what you would say is true, is TEs should actually be modular. At least we had the discussion about the program before. And we think this combination of TLS and remote attestation is also modular and fits the scheme. And we use this message extension, so we don't change the standard. Maybe it can be used without standardization because extensions already exist, but having it in the standard makes it even easier to use. So we can support independent root of trust. So it's not fixed to one. I didn't talk about that. Independent deployment I mentioned, and the interesting property for us is actually this independent failure, because we think that results in truly additive security. So you don't lose one if the other fails, and that's kind of a nice property, which hopefully someone can also formally prove to be the case. Yeah, so that was it. Thanks. Yeah.
The question you will hate performance.
I don't. Well, I don't really hate it, so I'm kind of. Yeah, so I wasn't sure about how much time I had. But yeah, so obviously it adds overhead, but this overhead is basically coming from all the attestation stuff. So the cryptographic operations, talking to the root of trust and so on. So this is the diagram on the left-hand side. So the white bars on the left of each of these pairs, that's plain TLS without any attestation, and the bars at the right are then doing what I described with various roots of trust. So that we have AMD SEB on Amazon Cloud Service, some instance, I forgot about which one. Then we have terminal TVM and some standard PC, and then DTVM is a discrete TVM on the Raspberry Pi. That's also why it's so slow. And the right-hand side is, this is part about the not added encryption, so it's basically TLS, so the performance is more or less the same once you start transmitting data. And again, the Raspberry Pi is extremely slow because there was no hardware acceleration in OpenSSL. That's fixed now, but the version we use was to. So it's, but I think you have to pay this for all the protocols, but at least it's not added network latency, although the message just gets slightly bigger. So we did see a few artifacts there, but it's,
Okay, quick follow-up question. What evidence are you gathering from TVM? Is it a quote or was it something like that?
It's basically a quote. Yeah, so it's not, it's a prototype, it's not a secure. So we have implemented this as a companion library to OpenSSL that hooks into the message handling, creating extensions and evaluating them and so on. And then it basically talks to the TPM. It's requesting a code for some. It's also checking the code, but this is actually implemented in software and the TSS. And yeah, so we just have some measurements, including something.
I guess it quotes, so.
Yeah, it's definitely slow.
Thank you.
I don't know yeah.
Are these numbers one single session or multiple?
Yeah, it's one single session times 10, 100, 1,000. It's so I think it's 10 iterations for the throughput and 100 iterations for the.
But they're not parallels.
They are not in parallel. Yeah, so it's. Yeah,
it's just usually bottleneck is on access for signature.
Yeah, it's a worst case because those are running on the same machine. That's why we did it. We wanted to really measure the worst case. So communication overhead, the network is loopback networking, and it's as fast as it can be. So if you have the internet in between, it might look more favorable. But this is the worst case overhead. I think there was another question. Are we on the question? Yeah, that's just one.
So, Radha, please go ahead.
Yeah. So in the conclusion, you said that TLS and remote attestation are root of trust independent.
Yes.
How is it independent of the root of trust?
Yeah. So the way we integrate this piggybacking of messages of remote attestation into those extensions, the mechanism doesn't care about the data that is being shipped. So we treat the attestation evidence as an opaque piece of data. It's just a byte array. So it can be anything. And this is what we basically did. So we had this for AMD SEV, we had this for TPMs, and we also had people at ARM doing this with a CCA emulator, which is not in this paper in the performance measurements because it's not public. So it's just a piece of data. Obviously, we then have to have plugins that know how to talk to SEV or to CCA or a TPM.
Do you check that it is the good evidence that is included, that it's not that the evidence that you include in the TLS exchanges comes really from trusted root of trust? Do you check this?
Yes, so there's so we actually check it. So in the prototype we have a whitelist of endorsed values and so on. But yeah, so we check the signature.
Thank you.
Yes.
You go back to the start when you talked about the 6 dimensions of these.
Yeah, so this scrolling wrong.
I think 10, it's like 10, it's like 8, yeah. What?
8? Yeah, okay, yeah, whatever.
So I guess maybe I'll just answer myself, but the way that I'm also working on some more modularization of these. And as a cryptographer, the way I'm thinking about it is kind of in terms of like what features apply to me and what attacks adversary can, so a feature could be something like, my TCP architect across the top, or it has access to the VPN to do like counters or whatever. Do you think that could fit in one of these 6 boxes? Or is that?
If I understood you correctly, what you're looking at is slightly orthogonal to this. So these are functional building blocks that you need in order to have the whole thing.
Yeah.
But obviously you have features in each of those boxes. That's why we think they should be differentiated. That's why I changed the colors here. So you could have various implementations that have different features. And of course, then there are also different attacks depending on what kind of isolation you have, how your root of trust is working. Is it sensitive to timing zap channels, or is it using the wrong type of signature key? So I guess it's orthogonal. I think you would work in multiple of these boxes, maybe also across the boxes.
Yeah, no, that makes sense. Yeah, that's an interesting way to